And welcome everybody. Woohoo! OSPF network types is the topic we're going to focus on today, and I am so glad that you're here to join me in this discussion about a lot about OSPF, and then also what the heck are OSPF network types and why do we care? Those are the two main home runs that we're going to focus on today. So to do that, I wanted to give a shout out to everybody who's joining us, especially Pat and Mike and Gus and others. I appreciate you being here as we take advantage of the time we have together to focus on, cool topics and maybe reinforce things you already learned or learn something new for the first time. So let's do this. In our goal of understanding OSPF, let's take a look at the whiteboard. And let me get out a pen tool here. And let's talk just for a moment about OSPF, or routers that we want to be OSPF neighbors. In fact, we should probably talk about what that means to be an OSPF neighbor. Won't you please, won't you please, won't you please, won't you be my neighbor? If we want routers to share information with each other, like, hey, what do you know? And what do you know? Let's share that information with each other so we can dynamically build routing tables. Building a neighborship or a full adjacency is when two routers, they agree on everything. They agree on what the subnet is between those two devices. They do agree, the mask is the exact same length, same network. They agree on things like what type of area is this? What is the network? Oh, we said that already. What else do they have to agree on? The timers. Like these little routers are going to send hello messages back and forth. And the timers have to be exactly correct, matching each other. Otherwise, they won't become neighbors. So the dead timers, they have to be the same on both sides. So another option is, do we want to have a designated router, yes or no, on this network segment? And all of those have to agree. And if they do, the routers will build an adjacency, and they'll become what they call, they'll have a full adjacency. They're sharing information back and forth. They care about each other, and it's a wonderful thing. So what if there were a few parameters that we had to negotiate, and we wanted to make sure we got them right every single time? That is one of the aspects that a network type in OSPF can help us with. And let's take a look at our topology, and then I'll do a demo. I'll show it to you in action. So let's imagine that, in fact, let's start with these two routers right here. I've got router 1, and I need to get my pen out. There we go. Why isn't my pen showing up? Oh, because it was white. That's so funny. It was white on white. My bad. All right, so let's imagine we have router 1 and router 2 that are going to become OSPF neighbors, meaning they're going to be able to share information with each other. To get that working, we need to do a few things. We need to go into router configuration mode on each of the routers. Router, OSPF, space, and then we use a process number. So if you are only running one process, you can use process 1 or process 10. It doesn't really matter. Press enter. That puts you in router configuration mode, and then we're going to add network statements. In fact, before we add network statements, I'm also going to hard code a router ID. And you don't have to hard code a router ID. It'll go ahead and choose the IP address that's the highest IP address on a loopback, if you have any loopbacks, or if you don't have those, the highest IP address on a physical interface that's up. But by hard coding the router ID for learning and also for documentation, seeing where things are, it makes a lot of sense. So I'm going to hard code the router ID on each of these devices, and then I'm going to use a network statement. Now, here's how a network statement operates. And a network statement in OSPF says to the router, "Dear Mr. Router, I want you to play a matching game." The router says, "What do you mean a matching game?" He says, "Well, here's what I want you to do. I'm going to say network 10 anything. And what I want you to do, Mr. Router, is I want you to look at all of your interfaces that are up. And if the network statement says 10 anything, I want you to take a look at all the interfaces that start with the IPv4 address of 10, doesn't matter what the rest is, and include them as part of OSPF, meaning you'll send updates and do hello statements back and forth on those interfaces." So the router says, "Okay, I get it." And that's what the network statement does. It tells the router indirectly which interfaces based on their IP addresses should be included in OSPF. So if we use the network statement like this, network 10.0.0.0, if we wanted to tell the router, you know what, just match on this first 10, we don't care about the last 3 octets, we would use what's called a wildcard mask. And a wildcard mask we use in many places, including OSPF network statements and also in access control lists. We use them as well. So a wildcard mask goes like this, 0 dot. Now that 0 here in the wildcard masks means we care about the first octet, and then we add the last 3 octets as wildcards. So effectively, anywhere it says 255, it means the corresponding octet right here. I don't care what it is. Right here, I don't care what it is. Here, I don't care what it is. We can call the bits that are on I don't care bits. And so that is how you tell a router that any interfaces that have that begin with the 10, number 10 of the first octet, those should all become part of OSPF. And then the other thing we need to add too is because OSPF can have multiple areas, you know, sometimes we need to carve things up to get stuff done. Like we have a huge, like cleaning our house. I don't know why that comes up for me right now. But anyway, if we have to clean our house, to do it all at once, it's going to take a lot of effort. So what we could do is we could take chunks of it. Like, okay, I'm going to do this part of the house now and this part of the house later. Or if we had guests over and we were memorizing other people's names, have everybody memorize everybody else's names, that's a lot of work. So we could say, okay, you're group A, you memorize each other's names. And group B, you memorize each other's names. And group C, you memorize each other's names. And in OSPF, we can quarantine or group our routers in networks into groups, and they call those areas. Just that a single router doesn't have to learn everything. It can just learn the routes in its area that's in, or a couple of the areas that it's in. So the other thing we want to do here is we are also going to add, when we do this network statement, we're going to specify what area those interfaces and those IP addresses should go into. So in our topology here, I'm going to specify that on router 1, any interfaces that start with 10, they should be put into OSPF, and they should be put in specifically into OSPF area 0. So that's how that plays out. And then I'd like to do is show that to you. Let's go ahead and let me hide the screen for a moment. And let me bring up an interface. And I need to log back in. And let me do this. I rearranged my screen, but let me close window. Let me line this up again. I was being clever and it bit me because I have to relog in. All right, my bad. Let me bring this right over here. Fantastic. Put in the password. And right here we're on router 1. So on router 1, we'll go into configuration. Actually, you know what we should do first before we configure OSPF is we got to verify that it's not already running. Show IP protocols. That'll show us if we have any dynamic routing protocols running. We don't. That's great. So we'll go into configuration mode, router, OSPF. We'll use process ID 1. Lots of choices there. And then I'm going to set the router ID. And on router 1, I'm going to use 1111. So it looks like an IP address. It's a 32-bit address in binary. So you can specify whatever you want the router ID to be, looking like an IP address. And then we'll go ahead and add our network statement. So network 10.0.0.0 space, and then we care about the first octet being a 10, and we don't care about the second octet, don't care about the third octet, what's there, and don't care about the fourth octet, space, and then we'll put those into area 0 just like that. Now, it's one thing to do a network statement, and it's a totally separate thing to verify which interfaces are now in OSPF because of that network statement. So a really quick, easy trick is do show IP, OSPF, interface, brief, and that will show us the interfaces that are now in part of or installed as part of OSPF. So it got on router 1, gig 2.0, gig 1.0, and gig 0.0. Fantastic. And it's in a wait state because those are all 3 of those networks are Ethernet. And so it's waiting to see whether or not there's a designated router on those segments. And when it finds out there aren't any, it'll win the election and it'll become the designated router here in about 15 to 20 seconds on each of those interfaces. All right, so that's router 1. Let's go ahead and do the same thing for router 2 in our topology, so I don't leave anybody behind. Let me bring back the images here. So on router 2, we'll do the same thing. We'll go into router OSPF, create the process, specify the router ID, and we'll also tell it that any of its interfaces that begin with 10 should become part and participate in OSPF as part of area 0. So we'll go back to our interface. And here we go, show IP protocols. Always a good idea to verify which router we're on. Make sure that our product isn't already running like OSPF or something else, because it's never a good idea to start configuring, making changes, then realizing, oh no, wrong device. So here we are on router 2, config T, router, OSPF 1, And we're going to do a router ID of 2222. And then we'll specify a network statement. Network of 10 dot anything, which is spelled like this. And we'll pump those into area 0. And to verify that, we'll do a show IP OSPF interface brief, just like that. And we have a point-to-point link, and we have the 3 others that are waiting, but we won't have to wait too long. On that one, gig 2/0, it's now a backup designated router. So what we have is a relationship. If we do we'll look at the neighbors, we can do a show IP OSPF neighbors. And this is showing us from R2's perspective, it has a neighbor, and that neighbor has the router ID of 1111, and its process is 1. And our current state with that is we have a full adjacency, and this /dr says that that neighbor is the designated router for this network segment. And that neighbor's address that we're reaching them on is 10.12.0.1, and it's our local 2/0 interface that we're using to reach him. So that's right here. Let me put the pen back up. So effectively, R2 says, oh, I see the neighbor relationship between myself and R1 over this interface right here. And that's because they agreed. They agreed on several things that are worth talking about here. They agreed between them on this network segment. They agreed on the actual network, meaning, oh, that's the 10.12.0 network with the 24-bit mask. They both agreed that between them, that network was in area 0. In fact, I'll spell this out. Network 10.12.0.0 with the 24-bit mask. They also agreed on hello and dead timers. Now you might say, Keith, what's a hello timer? How does that work? Well, when these neighbors care so much about each other that they are periodically going to send hello messages back and forth across that link, and they're expecting that those hello and dead timers have to match. So by default on this type of network, the hello interval is 10 seconds, and I'll put H here for hello, and the dead interval is 40 seconds. And so if one of these routers doesn't see the other's hello message, and they don't see it within 40 seconds, they're going to assume that neighbor is dead, no longer there, and they'll have a little funeral, and they'll move on with life. He'll realize that neighbor is no longer there. So that's what the hello and dead time, they have to agree to on what those are going to be. And then the other thing is to DR or not to DR. They have to agree on that. Now let's talk for a moment about what a designated router is all about, because this is a good discussion, and let me use a slightly different color for that. I'll use black. So let's imagine that we have a network segment right here. I'm just going to put this off in isolation land right here for a moment. So we have a network segment, and on this network segment, we've got many routers. I'm going to do a little overkill here, but 1, 2, 3, 4, 5, 6, 7, 8, 9, and we'll put 10. So we have 10 routers on this segment. Now, Ethernet is broadcast based, and these guys can all find each other dynamically. It's all wonderful. But if router 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's imagine that router 1 is going to build an adjacency, a neighborship, a full adjacency with R6. And R1 is going to form a full adjacency with R7 and R8 and R9. And R10, and R2, and R3, and R4, etc., 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 etc. That's not so bad by itself for that one device to form all those adjacencies. But if we do that also from every other device, so 5 to 10, 5 to 9, 5 to 4, etc., so we have a full mesh. Everybody has these full neighborships with everybody else. That also is, we could survive that. The problem, however, is that once they have these neighborships, what does a good neighbor do? Well, a good neighbor lets you know when stuff happens. And so if we have a change in the network, every neighbor is going to have to tell every other neighbor about that change, and the updates are just going to be crazy. We really don't need, on an Ethernet segment like that one segment, we don't need to have 10 full adjacencies between those 10 routers. It's just too much redundant overhead. Like, yeah, I heard about that from Joe. Yeah, router 5 told me. So what we do on networks like this, where we have multiple devices on the same network, is we elect a DR, a designated router. And I'd like, let's go ahead and put this in personal terms. let's imagine that we've got Mike, and let's also go ahead and pick Gus. So, and let's imagine we have a room full of 10 people. Now, in this live stream, we have a lot more than 10, but let's imagine we have 10 people in the room. And Mike and Gus got there first. And Mike says, hey, I'm the first one here. I don't see a clearinghouse for all these updates. I'll become the designated router. So it listens. There's no other designated router. It becomes a designated router for this room, this segment. And then Gus shows up about 90 seconds later and says, okay, I'm willing to communicate. I want to become neighbors. And he says, Gus says, Mike is already the designated router. And because I showed up after, he's already in place. Gus becomes the backup designated router. And they establish a full adjacency. So they are like glue. Anything that happens, they update each other. Life is good. Now, what happens when the third one comes in, the third device, and I'll play that role. When I show up on this network, I jump in, I power up, OSPF is now running. I say, I see these messages on this broadcast network. I see that we have a DR, which is Mike. I see that we have a backup designated router, which is Gus. I'm going to form a full adjacency with both of those guys because the designated router is like the clearinghouse for that network. He's like the go-to guy. By the way, thanks, Mike. And then Gus, if Mike goes away, Gus is like the backup who, if there's a problem on the network and Gus has to take over the role of designated router, I also want to have a relationship with him. So at the moment, we have full adjacencies. DR's fully adjacent with everybody. The BDR, which is Gus, fully adjacent with everybody. And me, I'm not a DR or a BDR. They call me a DR other. So if you see a router with the status of drother, like DR other, that's somebody who wasn't the DR, wasn't the BDR, but happy to be there. And he's establishing relationships with both of them. Now, here's where it gets interesting. The fourth device comes in. And so I'm going to write this down so I forget. And let's say the fourth device is Pat. So Pat comes on the network, has an interface on that network, has been enabled for OSPF. And Pat says, hey, okay, what's going on the network? I see we have a DR. I see we have a BDR. And what Pat does, he establishes a full adjacency with the DR, which is Mike, and the backup DR, which is Gus, because that's the clearinghouse for any updates regarding that network segment. They're going to come from the DR and BDR. And the BDR is there for backup purposes in case the DR goes away. And then then Pat says, whoa, we have this other guy here. I see him, this Keith. He's not the DR. He's not the BDR. He's a DR other. And so he's aware of me, and I'm aware of him, and we will establish what's called a two-way state. It just says, I know about Pat, and Pat knows about me, but we are not fully adjacent. We're not going to update each other because we're both getting updates from the designated router. And that continues on as the fifth and sixth and seventh and eighth device comes in. Everybody establishes a full adjacency with the DR and BDR, and everybody else who's not a DR or BDR, a DR other, are going to form a two-way state, which is basically saying, I know about you, you know about me, it's all cool, but we're not going to do updates between us because we have the DRs in place. Okay, so how does that affect a network type with OSPF? And here's the answer to that question. When we have an interface that is Ethernet, the network, an Ethernet network, we have 10, like say they have 5 or 6 devices plugged into one VLAN. If one device does a broadcast or sends a multicast, everybody else on that same network segment is going to be able to see it. And that's considered a broadcast-based network. That's how Ethernet works. It's broadcast-based. And so with OSPF, if we enable OSPF by doing a network statement, which implies also that the interface that has that IP address becomes part of OSPF, if it's Ethernet, the default network type is broadcast. The default OSPF network type is broadcast for that interface. And here's how that helps. It helps because it says to everybody on that network segment and this device also, hey, this is a OSPF network type of broadcast. That means that broadcast can be seen along with multicasts on this network segment, and we're going to have a designated router, and I don't have to manually form my adjacencies. I can send out broadcast and multicast messages more appropriate with OSPF, and the neighborships will form automagically. We don't have to manually say, he's the DR, he's the BDR, here's his priority. We just enable OSPF, and because the network type of broadcast says, yep, allow the neighborships to form automatically, and has default sets of timers. So check this out, what we just did. By enabling OSPF on these Ethernet interfaces, we just locked in the hello and dead interval because it saw this Ethernet interface as a OSPF network type of broadcast. And it also identified that we don't have to manually assign neighbors because they'll dynamically find each other. And we also identified, because the network type of broadcast assumes that we're using a designated router, these two routers are assuming that there needs to be a designated router and backup designated router for that network statement. So that's how the network statement, the OSPF network type, is assisting us with OSPF, is because it takes the timers, whether or not to use a designated router, and it puts in a bunch of defaults for those based on the network type. So in review, if we have an OSPF router and it has an Ethernet interface and we enable OSPF on it, by default, the OSPF network type is going to be broadcast, which means the hello and dead interval timers are expected to be a certain value. The OSPF is expecting that neighbors can be dynamically discovered, and then if there's a broadcast or a multicast sent, it's going to be seen by everybody else on that network segment. So, and there's going to be a DR on that segment. That's all those things are meant by the type network statement of broadcast, and it's by default with Ethernet. So if we took a look at that, let's do that now. Let me go back to the screen, hide that for a moment. And let's take a look at this interface right here, gig 2/0 on R2. That's this interface that's connecting from R2 over to R1. So we'll bring up the interface. I'll log back in. And to see the actual interface type, we'll just show IP OSPF interface gig, and 2/0 is the interface. There's quite a bit of output, but it's manageable. So right here, it's indicating that for that interface, that the network type is broadcast. And again, broadcast means, okay, here's these certain set of hello and dead interval timers, and we can dynamically find each other, neighbors. We don't have to manually configure neighbors. And the on this network, we're going to be assuming that there's going to be a designated router and BDR if there's more than one device there on that network segment. And that's how it helps us. And so if we looked at R1, let's go ahead and do that. On R1, if we do show CDP neighbors, that's when I get the right interface. So from R1's perspective, the interface going over to R2 is gig 1/0. And so if we did a show IP OSPF interface for gig 1/0, it would also show us that because it's Ethernet, by default, the OSPF network type is broadcast. And as a result, we're expecting to use DRs, we're expecting hello and dead interval timers of a certain parameter, and we're also expecting that we can dynamically discover each other and other devices on that same network because it's broadcast based. So that's what the OSPF network type of broadcast is all about. All right, so here's what I'd like to do next. When might that be a problem? That's what I'd like to talk about, because that's where it gets interesting and dicey. When would a network type of broadcast be a problem? And I think what I'd like to do is do some chalk talk with you, and then we'll elaborate and say, oh my gosh, I can see why broadcast would not work in this scenario. And that's why we have some other network types besides just broadcast for OSPF. So let me go ahead and hide that, and let me bring up a white chalkboard. This one would probably work great. Yes, it will. All right, this is gonna be a fun dialogue here. Let me do that. Let me bring up one additional layer. Lots of bells and whistles. Okay, so let's go ahead and take this network here, and we'll put some routers there. You get the idea. We have several routers. And this is an Ethernet network. Now, an Ethernet network is considered a broadcast network. And it's simply a broadcast network because if this device right here sends a broadcast or a multicast into this network segment, which of the other devices are going to be able to hear that? The answer is all of them. They're in the same VLAN, same layer 2 network and the same layer 3 IP address. So we have the same IP subnet, and it supports broadcasts, and the hello intervals for OSPF on a broadcast network type is 10 second, the dead is 40. So it's great. So if we bring all the routers up, we enable all those interfaces for OSPF. By default on Ethernet, it'll say this is the network type of broadcast, and the factors of the hello and dead interval and the fact that the neighbors can be dynamically discovered, all of that works. So over here on the far left, to keep it nice and simple, I'm going to put network type OSPF, and then I'll put here broadcast. Just like that. All right. And then I also am going to put here dynamic neighbors. So all that means is that these routers, once the OSPF is enabled and they agree on the parameters, they can dynamically discover and associate with each other. Life is good. All right, let me put also on the OSPF network type of broadcast, we are going to be using designated routers and backup designated routers because that's how OSPF works on a broadcast network. So let me go ahead and put a little line there. And I would like to, I'm going to go back in the time machine with you for a moment because this is where all this came from with the other alternate network types. Back in the 90s, when I worked for Paramount Pictures, a long time ago in a galaxy far away, there was this new WAN technology. It's like in the early days, like in the 80s, we used dedicated leased lines. I worked for Blue Cross of California back then. We had dedicated leased lines between Northern California and Southern California. It was fascinating, because we had time division multiplexing on these T1 circuits. A lot of fun stuff. But then this new thing came out called frame relay. So it's a packet switch network, and with frame relay, you could just buy logical circuits, and you don't have to pay for the entire dedicated circuit, so the cost was amazing. Also, there's a lot more flexibility. So frame relay, about 20 years ago, was the cat's meow. And so we had situations with frame relay that might look like this. So we'd have the headquarter site, and we'll call the headquarter router 1, and then maybe have sites 2 and 3 and 4. And they all had routers there as well. And then for connectivity, we would have, I'll just draw a line. We would have connections like this. And so with the frame relay cloud, these would be representing PVCs, permanent virtual circuits. They're identified with the data link connection identifier on both sides. And I got to tell you, in preparing for this today, I thought, I get to go back in the time machine and I'll show them how to do frame relay and I'll show them how to do dulces and the mappings. And I thought to myself, stop the truck. Network types with OSPF, a lot of the creative ones were built because of frame relay. However, we are going to see very, very little frame relay on any networks that have been around for a year or two or in a decade, because frame relay is a very old technology. Now we have like Metro Ethernet, and we have MPLS Layer 3 VPNs, and all the other SD-WAN, all these other really cool options. So just a little history on where this came from. And 20 plus years ago, frame relay was the king of the hill for WAN circuits. But that brings us to this network type right here. So if this is, let me get a different color out here. Let's imagine that this represents network 10.20.0.0/ and let's use a /29. That'll work. So we use a /29, and then these are all one logical network. But so the connections, the PVCs, would go from router 1 to router 2, router 1 to router 3, router 1 to router 4. Now, what I want to point out is that this would be referred to as a multi-access network. And so with this, by the way, you might say, Keith, what is a multi-access network? A multi-access network is a network where the IP subnet can support more than just 2 people. So if it's 3 or more, if the IP network supports 3 or more, and the same subnet, that can be considered a multi-access network from the purposes of what we're discussing with OSPF. So in this case here, if I've got the headquarters site, and then off to the edges, they've got site 1 network, and then site 2 network, and site 3 network. if this is just one network, this is a multi-access network. But here's my question. If router 1 sent a broadcast, who would hear it? So router 1 sends a broadcast or a multicast. In the case, and also I want to point out, in the case of when we're talking about OSPF, we're talking about broadcast networks. Also consider that to be almost synonymous with multicast networks, where that message would be received by everybody else on the network. So if this headquarter router, router 1, sent out a broadcast or a multicast, it would be seen by router 2, router 3, router 4. I'm thinking, home run. Yeah, done. Got it. That multicast, that broadcast was seen by all the other devices. No problem. Until we see about router 2 or router 3 or router 4 and having them try to do a broadcast or a multicast, because it gets dicey then. See, if router 2 sends out a broadcast or a multicast into the network, who's going to hear it? Because I'll tell you what, router 1 is a router. It is not a bridge. It's not a switch. It's a router. So the problem here is that we have this multi-access network, but it does not support. I put support. Hold on a second. It does not support broadcast. And what would we call something like this? A multi-access network that doesn't support broadcast. Well, there's a couple names we could think of it. I could think of one like NBMA, a non-broadcast multi-access network, which is exactly what this is. And in OSPF, we have several ways of dealing with this. One is an OSPF network type of non-broadcast. And let me tell you what that means. So if we had a frame relay circuit, which you're going to be hard-pressed to find one these days, but if you had a frame relay circuit and you had your DLCs and PVCs configured like this, when you configure this interface here, by default, OSPF would say, oh, this is encapsulation frame relay, and it would by default use a OSPF network type when OSPF is enabled of non-broadcast. Here's what non-broadcast means, because we're still getting the same benefits as far as having an agreement between the devices. Non-broadcast means that we are still going to be using a DR and BDR. And let me go ahead and spell that correctly. Shouldn't be too hard with a 3-letter word. So that's a yes, yes. So the broadcast network type uses a DR and BDR. The non-broadcast type uses a DR and BDR. But here's the difference. Instead of having dynamic neighbors, you have to do it manually. And that involves going to the router process and manually specifying from router 1's perspective, my neighbor is and router 2, and my neighbor is and router 3, and my neighbor is and router 4, and you have to manually assign the neighbors. So this is an example where non-broadcast would be used, and non-broadcast in this sense basically means that the neighborships would be assigned manually, and the hello and dead interval for the timers, the default for those is 30, and I think it's 3 times that, 4 times that, 4 times, yeah, I think it's 4, maybe it's 120. We can check that for sure. But so the non-broadcast uses the DR, a BDR, it's expecting manual neighborships, and the hello and dead interval timers change a little bit. But that's okay. If router 1 and router 2 and router 3 and router 4 are all manually configuring neighborships, the timers are all going to match, and life goes on. No problem. Now, for me, and most people, it is a pain to have to set up these neighborships, manually specify who your neighbors are. And so Cisco also has a solution for that. And I will go ahead and put a little line right here. And we're going to use the same topology again. So we still have this multi-access network, but we can use this network, OSPF network type of point to multi-point. And with a point to multi-point, I hate to say it, but this is the death right here. Death of doctors and BDRs. So anytime you have a network type that has the word point in it, it's not a bad way to remember, by the way. If your network type has the word point in it, point to multi-point, non-broadcast, point-to-point all by itself, that means you're no longer using a DR. And it's cool. If both devices or all the devices on the network segment say, yep, we're going to be using point-to-multipoint, none of them are expecting a designated router. They all agree. The timers are going to be associated as the same value with a point-to-multipoint, and it's good to go. So point-to-multipoint is a good option in this old frame relay configuration to avoid having to use a DR and have more of an agreement. There's also some tricks that are going to be used as the leafs, the remote sites, or I guess over here, the remote sites, advertise and forward information. There's some next hop trickery that goes on to make the actual packet flow work better. That's beyond the scope of anybody. That's beyond the scope of most people who would care because we're not using frame relay anymore. But that's another side benefit of point-to-multipoint. So with point-to-multipoint, no DR. We have auto. I'm going to change my color here. Let me back up a second. Dunk, dunk. Auto neighbors, which means if you've got your infrastructure set up correctly with the broadcast option on your data link on your PVCs, that the neighbors will automatically be able to identify each other. You don't have to manually assign the neighbors, which is great. So dynamic neighbor discovery, the timers, the hello timer is 30, and the dead I think is 4 times that. So I think that's 120. We could just confirm that, but whatever it is, it's the same on both sides, and that's fantastic. And then somebody came up and said, you know what? I love it. Point-to-multipoint, great, except in my infrastructure, my PVCs with this really old technology with frame relay, my PVCs don't support the broadcast option. So I really like the point-to-multipoint idea, but they don't support this broadcast feature on each of the DLCs for automatic discovery. And Cisco said, no problem. We'll give you another option. And that is point-to-multipoint, non-broadcast. It's like point-to-multipoint, except you have to manually assign your neighbors, just as you had to with non-broadcast. That's all it means. So coming back here, I'm going to add the option right here in a bracket. Non-broadcast. And if we do non-broadcast, that means, once again, manual neighbors. So you might think, well, no, I'm not going to go there. It's like really, really likely you'll never, ever, 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 ever have to do this. But I wanted to point out where this point-to-multipoint comes from. It's if you have a non-broadcast multi-access network with something like ATM or PVCs with frame relay behind it. The point-to-multipoint is a wonderful solution for that, unless your PVCs don't support broadcast, and then they have for the non-broadcast option, which says, hey, it's like point-to-multipoint, except you have to manually add your neighbor statements once again. But in either case, they don't use a DR. Now, those are four different OSPF network types. And the reason they come in handy is that several of the parameters are pre-baked that both sides can understand. Like, should we use a DR or not? Great. It's decided if you're using the OSPF network type that's the same on both sides. The timers are going to be the same on both sides. So whether or not you have to manually add the neighbor statements for OSPF depends on whether you're using a network type that says you have to or not. So the non-broadcast option, when it shows up, means you have to manually add your neighbor statements for OSPF. So there's one final network type, I'm looking at the screen here, that I want to chat with you about, and that is point-to-point. Now, a point-to-point network is not multi-access. It's the only one of these that aren't. So a point-to-point network means there's two devices, one here, and that's it. So Ethernet, you could have multiple devices on the same subnet, but point-to-point, that IP network is just two devices. There's no room, no options for anything else. So how does your router know if a network segment is point-to-point? The answer is it looks at the layer 2 encapsulation. If the layer 2 encapsulation is Ethernet, it says, hey, broadcast network for OSPF. Yeah, it's right. If it looks at the interface encapsulation on a serial link, for example, it says, oh, this is HDLC, or it's point-to-point protocol, it's point-to-point, and it defaults to IP OSPF network type of point-to-point. Now, we can override those, and there's not really a lot of great reasons to do so, But we can actually go in and override those defaults for the network types. But that's how it knows. So let's put in the last one here, which is, and I'll put a little line here, point IP OSPF network type of point to point. And it would look something like this: router 1, router 2. And then you have on this link. Now, if this was Ethernet right here, it would not be by default a point-to-point OSPF network type. It would be broadcast. So if this was a serial link and we are using encapsulation PPP on both sides, or if we were using encapsulation HDLC on both sides, and if we went really way far back in the archives for frame relay, and we created a frame relay subinterface, we could specify a point-to-point subinterface in frame relay. But it's based on the encapsulation at layer 2 that's controlling what OSPF network type it's going to be. So what I thought would be fun to do is, let me see if I can find, bonk, there it is, not too bad. Let's go ahead and let's configure the rest of these routers 3 and 4, because we have the serial link, and because this is using PPP, I believe, between them, it'll automatically on this interface, it'll show up as IP OSPF network type of point-to-point, and with point-to-point, the hello and dead timers are set to 10 and 40, and they're not looking for a DR at all because it's point-to-point. So let's do that. Let me finish the around the horn, and then we can take a look at the interfaces, and then if you want, we can actually tweak and play with them and change them and still make it work. The OSPF network types do not have to agree as long as they agree enough. I mean, for example, both sides have to agree whether or not there's going to be a DR on that network segment. That's one thing that has to be agreed upon, and the timers have to agree. But we could have broadcast and non-broadcast on 2 different routers, and then we could manually manipulate the neighbor statements and make them work. But you know what? It's better just to understand how it helps us use the network types that are there and then move forward. So let's configure the rest of our network. So to do that, let's go down here to this bad boy. All right, so just to remember where I am, let's do a show IP OSPF interface brief. Here on router 1, okay, it's great. Oh, look, it's the DR for each of its Ethernet segments because it was the first one up, and it won. And then here's R2, show IP OSPF interface brief. Great, and show IP OSPF neighbors. Great, he's got a neighborship with R1, but not with anybody else, and that's because we haven't configured R3 or R4 yet. So let's go around the horn. Let's configure R3, just to remind you where that is. R3 is this guy right here. So we'll configure R3. Show IP protocols, nothing running yet. Show IP OSPF, nothing there. Great, config T, router OSPF. Router OSPF process ID 1, router ID 3.3.3.3. Great, and network 10.0.0.0, and then wildcard masks for the last 3 octets, and we'll drop all of those into area 0. Just like that. Wow, I pressed enter. There we go. Come on, you bad boy. All right, and wow, it's poking along there. All right, show IP OSPF interface brief. All right, and let's do router 4 as well. So here on router 4, config T, and router OSPF 1, router ID 4.4.4.4, and then our network statement. Wow. Okay, it's going to be the 10 network, and then wildcard mask for the last 3 octets because we want, it's not going to like that 8 in there. Let me fix that. Control E to go to the end and put those into area 0. All right, and a quick check. We'll do a show IP OSPF interface brief. Yeah, we got a new neighborship with R2, fantastic. And a new neighborship with R3, that's fantastic. And then we do a show IP OSPF neighbors. and that should show us neighborships. I'm thinking with we're on R4. Oh yeah, with R2 and R3. Fantastic. All right, let's go over to R3, and just so we know where we are on the topology, this is R3 right here, and I'm expecting on this serial interface, serial 3/3, I'm expecting that interface type to be IP OSPF network type of point to point, and that's because of the encapsulation that's on that serial interface. That's the whole reason. So if we go up to that and we do on the right router, show IP, show IP OSPF interface for, I'm having some serious lag problems, not sure what it is. All right, show IP OSPF interface, serial 3/3, and survey says, all right, so here's the command I issued. Fantabulous. And right here it's showing that the network type is point to point, and for that, and let's take a look at the interface encapsulation. Show interface serial 3/3. Oh my gosh, I have no idea why this is lagging so bad. Oh, there we go. Maybe it knows I'm doing a demo. Okay, so there's just the raw output from show interface serial 3/3, and the encapsulation is PPP. So that's the reason, from an OSPF perspective, that it used the OSPF network type of point to point. So if we wanted to change any of these, we could. If we go into configuration mode, interface serial 3/3, and type in IP OSPF network, and then do a question mark, we have the options for broadcast, which uses the DR. We have non-broadcast, which doesn't use a DR, and you have to manually specify your neighbors. We have point-to-point, which doesn't use a DR. We have point-to-multipoint, which doesn't use a DR. And then if we do point-to-multipoint, there's also a following option of non-broadcast, which means we would also have to manually specify our neighbors for OSPF in that interface if he's the point-to-multipoint non-broadcast, which is the 5th OSPF network type that we've talked about. All right. Let me see if that's everything I wanted to talk about with you. The major focus in today's session was to take a look at what are OSPF network types, and we've identified 5 of them. 3 of them, 2 or 3 of them you probably never ever have to use, and also what the benefit is. And the big benefit is that there are some defaults in place. On Ethernet, it's going to be a broadcast network type. On HDLC or PPP serial link, it's going to default to a network type of point-to-point. And the benefit of each of those is there's pre-agreements on whether or not we're going to use a DR or not. There's pre-agreements on what the timers are going to be for the hello and dead intervals. And so then we just have to get the other parameters correct, like the network length and the area that that network is in, and authentication, and a few other details just to make sure that OSPF will then form the adjacencies. And if it's just a DR and a BDR, they'll form full adjacencies. The 3rd device in will also form full adjacencies. But that 4th device in will not form a full adjacency with the other DR other, but it will form adjacencies with the DR and the BDR, which were happily played by Mike and Gus in this analogy. So that's what I wanted to cover today. There is a lot to OSPF, but I wanted to focus on, again, what is a network type for OSPF? What are some of the defaults for it? And how does it help us? And I think we did that as well. So, you know what? Let me do this. I haven't had even just a moment to look at the queue. I appreciate a lot of people helping each other with questions and answers. I'm going to put some music on just for maybe 1 minute, maybe 1 minute and 10 seconds. And I'm going to take a quick look at the queue, see if there's any burning questions that you want me to elaborate on. If you do have a question you'd like me to ask, if you want to retype it in, that way it'd be right there near the bottom so I can see it. And I'll be back in just a moment with your questions. Meanwhile, some music. All right, and some great questions and some great answers from the group. So thank you for that. One of the concepts or the clarifications was multicast. Now, when OSPF is speaking and they're doing their discovery and adjacencies and so forth, if we're on a network like a broadcast network, or if we're on a network that like point to multipoint that supports multicast, and when I say a broadcast, that's a frame that's sent from one device that can reach everybody else. The exception to that is point to multipoint, where you have like a hub and spoke topology. Multicast is used, local multicast, for those interactions. So if we have Mike and Gus, which are the DR and BDR, as we're sending information to them as DR others, we're sending it to the multicast address of 224.0.0.6. And as we communicate with all OSPF speakers, not DRs and not BDRs, we send it to 224.0.0.5. So if you have networks that are not non-broadcast, they are using those multicast addresses. So on point-to-point links, if we did a protocol analyzer, we would see a lot of traffic being sent back and forth to 224.0.0.5. Now, a 224.0.0 address is local. It doesn't get routed off the local network. So with IP multicasting, like with PIM and bootstrap routers and all that good stuff, we can actually route traffic streams across networks with using rendezvous points and using and PIM, protocol independent multicast. I'm not sure why I had a problem with that, but that's not what we're talking about with OSPF. We're talking about, OSPF does use a multicast address, but when they send out a multicast based on the type of network, it's the question, will that multicast reach everybody? And so on broadcast networks and point to multipoint, those are seen. And point to point, we just shoot them back and forth over that link. There was one other question that I saw. Oh, yeah. So great. The only one of the questions was, what's a real world application for using like a point to multipoint non-broadcast option? And that is only if you have to. So we don't have a lot of frame relay point to multipoint networks going in anymore. I mean, there's just better options that service providers have for us. They give you an Ethernet circuit and say, here, is it great? And then they do MPLS for you with layer 3 VPNs to connect your sites together. So the whole conversation about frame relay really goes back to 20 years ago, and there's not too much of an application for it anymore because we don't use those technologies anymore. Those are band-aids and solutions in the days when we had one device that had, like, at the headquarters site with multiple PVCs going to remote sites. When would we ever use so broadcast is a great solution for Ethernet. If we ever wanted to manually specify who our neighbors were, we could force everything to non-broadcast. That would work, but we then have to manually assign our neighbors, which is not fun. So the two main ones we're going to use today most of the time are broadcast based on Ethernet, and we're done. And then if we have a service provider doing MPLS layer 3 VPNs for us, we just shoot our traffic over Ethernet, and it's good. We may peer with our service provider using OSPF, but it won't be anything tricky. It'll be like one neighbor, the service provider at the edge, their provider edge, and we're talking to them. So great question. Okay, I noticed in my a few years back that the BDR always selected first before DR. I've never seen that ever. So at the end of the day, if you have only one device, it's going to be a DR, and then the second device comes up and it'll be the BDR, and they're never going to supersede each other as long as that DR is still in place. Now, if you have two devices that come up at the exact same moment, the interfaces have a default priority, and that default priority is 1. So if you have two devices that both come up at the same moment, they both have the same priority of 1 each, the one with the higher router ID is going to go ahead and win. And it'll become the DR for the segment, and the other guy will be the BDR, and then everybody else will just fall in after that. Another question I saw here was subnetting Saturdays, and the answer is yes. It is Wednesday today, Thursday, Friday, Saturday. In 3 days. I haven't put the outline I've taught subnetting many times, and I love it. So I'm going to put together subnetting Saturdays for probably a month and a half, fairly short chunks that somebody can just take in order and just ease into the idea. First of all, what is an IP network address, and what does the mask do, and then the binary behind that, and then why would we need to subnet, and then how to subnet gracefully. And I'm going to teach the finger game because worldwide it is loved. and it's easy. So if you're not the kind of guy who says, I love anything to the power of 0, in fact, I love powers of 2, you don't need to worry about it. I'm going to teach you how to do it without having to do powers of 2 or realize what 2 to the power of 0 is and why is it always 1. And yeah, I built that finger game and the ability to calculate correctly subnetting based on my lack of math skills, frankly. I'm not great at math. I mean, I have a high school education. I do. Woo! Best 5 years of my life. But yeah, when I learned subnetting back in the 80s, and I love it. And I thought to myself, as I started to teach to other people, I thought, we need a way that people can just understand this. You know, nice, easy steps, nothing mystical or magical, using your fingers occasionally to count and calculate what the correct subnets are. And that's starting. It'll be 11 a.m. Pacific time on Saturdays, starting this Saturday. Now, the good news is I built a playlist, and it is OGIT, Original Gangster of IT, .online. I had to think about that for a second. /sloth. Thanks, Mr. Sloth. I thought that's a really easy way to find it, and that's going to be plastered everywhere. So and I'll add these live streams in the right order into that playlist. So if you're ever like a couple months from now, you're thinking, what's new or what's there, just go to that playlist, go down the list, say, oh, that looks new and that looks new, and I want to rebrush up on that and so forth. Also, if you haven't already, sometimes we get involved in these live streams and I forget to invite you. If you haven't already, take a moment now and subscribe. That way you can get alerts and notifications when new stuff comes out. Hit the bell so you can become part of the family and learn alongside of us. All right. I think that's almost all of it. And Johnny Quad, I love my IP calculator too. All right. Hey, everybody, thanks for joining me. I'm going to cut this off right now. It's been just under an hour. I really appreciate the participation and the answering of questions. I believe anybody who wants to can apply themselves and not only get a CCNA, but also learn the skills regarding a CCNA. So when you walk into a job environment and they're asking you to troubleshoot, which is a big part of IT work today, you can say, yeah, I understand how this works. I have hands-on experience doing that. And based on X and Y and Z, there's your problem right there. And just solve it. And be part of a team that may be involved in solving it. Because it could be application layer stuff and networking stuff. And having people that can communicate and come together makes for a very happy team that's successful. All right. I'm going to go out with some exit music. So let me find that real quick. Here it is. Got it. And I look forward to seeing you in our very next stream and in the playlist. And until then, be well. And thanks for being here.